Let's do some more predicting of what the change in entropy should be for different things happening. And when you do this, just keep in mind that a higher entropy means more disorder. Versus lower means more order. So when you think about it, melting, it's going from a solid, which is very ordered, to a liquid, which is more disorder. So this way, that means an increase in entropy. In other words, delta S would be positive. Condensing is going from a gas, which has a lot of disorder, to a liquid, which has less. So this would be a negative delta S. Warming is always an increase in entropy. For a chemical reaction, one of the big factors in a lot of them is just to look at the number of moles of gas. A gas has a lot more entropy than a liquid or solid, so that can be, you just compare the reactants and products and see how many. We'll do an example. Another thing is if you see anything split apart, and this is the single most important factor, it doesn't come up all that much in our examples, but if you see like one molecule splitting into two, that is going to be an increase in entropy. Okay, so let's apply those to these, apply those rules to these. And so what I would do first of all is just look at the gas, because the gas is, moles of gas are changing. We have, this has 3 moles of gas, and this has 2 moles. So this is a decrease in the moles, so it's going to that's going to be a decrease in entropy. So our delta S sign is negative. Okay, and the same thing on this one. This one really kind of has 2 factors going on, but it's going from 2 moles of gas to 3 moles of gas. So more gas this way. Also notice that you have more particles. Here you have 2 particles, and here you have 3. 1, 2, 3. But anyway, so both of those, you're going to have a positive delta S. We already talked about that you could have entropy values for substances, kind of like we have heats of formation. And so that brings up the 3rd law of thermodynamics, and that is that, and this is just defined and it makes sense, that if you have a perfectly crystalline solid at 0 degrees Kelvin, so this is when all motion has stopped, we'll define that as having an entropy of 0. And so if we had our heating curve here, and in this case, instead of temperature, it's entropy over here, that this down here is 0 at 0 Kelvin when it's perfectly crystalline. Again, this is a lot like heats of formation, that when we define a 0, like we did for heats of formation, we define 0 as the reference form elements. In this case, we've defined our 0, and we can compare to that for everything else. So, so on this one, this little sign here means standard state. because we're not going to be comparing things at 0 Kelvin. That doesn't make sense. We're going to compare things at, I'm surprised we didn't have it here. It's 1 atmosphere and 25 degrees C. Here it has it here. That's our standard state for this. It's not like STP for gases. And then for solutions, we have some rules and so forth. But where this can come in handy is that then you can calculate the change in entropy for a reaction, kind of like we did for the heated reaction. We'll basically add up. The N is for the moles and its products, minus, add up all the entropies for the reactants. And again, this N you're going to get from the coefficients.